We have the central sulfur atom and 4 oxygen atoms around it. Looking at the Lewis structure, they do seem to be pretty spread out in accordance with valence shell electron pair repulsion theory. But remember, this is 2 dimensions, so we're going to have to look a little bit deeper in 3 dimensions to really figure out this molecular geometry. To help us, let's use the AXN notation to figure the molecular geometry for SO4 2-. A, that's the central sulfur. X, that's the number of atoms bonded to the central sulfur. We have those 4 oxygen atoms bonded. And then N, that's the non-bonding electron pairs on the central atom there. Well, all of the electron pairs are involved in bonds for the sulfur, so we can just ignore N. You could have memorized that AX4 is a tetrahedral molecular geometry, or if you have it available, you can look it up on a table. Going down our table, we see AX2, AX3, and there's AX4, which is tetrahedral, and those bond angles are 109.5 degrees. But remember, the view on the screen right now, the Lewis structure, that's 2-dimensional. We need to think about this in 3 dimensions. So this is one way you might see the 3-dimensional molecular geometry for SO4 2-. We can also use a model to help you visualize what that would look like. So that's the molecular geometry or shape for SO4 2-. This is Dr. B, and thanks for watching. Lewis geometry for CHCl3. A, that's the carbon in the center. X, that's the number of atoms bonded to the carbon. We have 3 chlorines and 1 hydrogen, so we have 4 atoms bonded to that carbon. And N, those are the pairs of non-bonding electrons. Well, all of those electrons on the carbon are involved in chemical bonds, so we're not going to worry about N. So going down our table here, we see AX2, AX3, and AX4, which is tetrahedral and has bond angles of 109.5 degrees. If we look at the tetrahedral molecular geometry here for CHCl3 in 3 dimensions, we can see what it looks like. Here the chlorines are the green. In the center we have the carbon, and the white is the hydrogen. So you can see we have all those chlorines on the bottom, and then on the top we have the white, which is the hydrogen. And they're all spread out as far away from each other as they can possibly be and still be attached to that central carbon. We can also look at the bond angles, which you remember are 109.5. So this angle right here is going to be 109.5 degrees, as is this angle up here, this angle over here, and then on the other side as well. This is a periodic table. Beryllium's in group 2, 2 valence electrons. Fluorine has 7, but we have 2 fluorines for a total of 16 valence electrons. Put beryllium here, it's the least electronegative, and the fluorines can go on the outside. So we have 16 valence electrons. We'll put 2 here between to form chemical bonds. We've used 4, and then around the outside. 6, 8, 10, 12, 14, 16, and we've used all our valence electrons. You can see right away that beryllium does not have 8 valence electrons, so it doesn't have an octet. The strange thing is beryllium doesn't really need 8. It's sort of an exception to the rule. So I could also draw beryllium fluoride a different way. So over here I'm using the same number of valence electrons, but by sharing I've created double bonds between the beryllium and the fluorine, and that gives the beryllium 8, while the fluorine still has 8 as well. So everything has an octet on this side. But which one of these is the correct structure? To answer that, we can use formal charges. So let's calculate the formal charge on each atom. We'll start with this fluorine right here. So fluorine on the periodic table, 7 valence electrons. Non-bonding, that's those guys right there. We have 4 of them. And then bonding, we also have 4. So we'll take 4 over 2. So 7 minus 4 minus 2 gives us a positive 1. So the formal charge for this fluorine is +1. And this fluorine over here has the same format, so it is also a +1. For the beryllium, we have 2 valence electrons minus non-bonding. They're all involved in bonds. And then minus bonding, 8 over 2. 2 minus 8 over 2 gives us actually a -2. So the formal charge on beryllium is -2. On this molecule, let's do the fluorine. So we have 7 minus 6 minus 2 over 2, that equals 0. So formal charge is 0. Same for this one, since it's the same. And then for beryllium, we have 2 minus 0 minus the 4 bonding electrons over 2. That also equals 0. So the formal charge here is 0. The most appropriate structure is going to be the structure that has a formal charge closest to 0. So in this case, they're all 0. That makes this the correct Lewis structure for BeF2, even though we didn't satisfy the octets. The structure here, we have the octets, but the formal charges tell us that this isn't going to be the probable structure. In order to determine the molecular geometry for H2O, first we need to look at the Lewis structure. You can see there are 2 hydrogens on that central oxygen there, but very importantly, there are also 2 pairs of electrons on the top and bottom of the oxygen in this Lewis structure. So, according to valence shell electron pair repulsion theory, those 4 things will spread out as far as possible, and that's what's going to give us our molecular geometry or our shape for H2O. In order to visualize that, let's look at it in 3 dimensions. So here's the water molecule. We have the red, that's the oxygen, and the hydrogens are the whites, and then the lone pair electrons, they're on top. So as we look at this, we can see it's not a straight molecule. It actually has a bent shape, and that's going to be the molecular geometry, bent. Let's go back, though, and look at another method to determine the molecular geometry. We'll use the AXN notation to figure out the geometry. A, that's the central atom we're dealing with, in this case the oxygen. X, that's going to be the number of atoms attached to the oxygen. We have the 2 hydrogens, so we're going to put a 2 here. And N, that's the non-bonding electron pairs. We have 2 pairs. We have 1 here, and we have 1 right here. So N is going to be 2 as well. You could have memorized that AX2N2 has a bent molecular geometry, or if you have it available, you could look it up on a table. So here in our table, we go down, we see AX2, AX3, all the way down AX6, AX2N, we're getting close, and there it is at the bottom, AX2N2, which has a bent molecular geometry, and the bond angles are going to be 109.5 degrees. Going back to our 3D visualization of the H2O molecule, we can see that the bond angle between the oxygens and the hydrogens is 109.5 degrees. So using both the valence shell electron pair repulsion theory and using the table where we look at the AXN notation, we figured out the molecular geometry for water.